Hello. In this video I will reveal the mystery about why Huckel numbers are good for molecules and anti-Huckel numbers are bad for molecules. In other words, what is it about the numbers that we refer to as Huckel numbers, or good numbers, 2 pi electrons, 6 pi electrons, 10 pi electrons, 14 pi electrons, and so on. Why are they particularly good to have in a delocalized or a conjugated system? Whereas the anti-Huckel or bad numbers, the ones that give rise to anti-aromatic for 8, 12, 16, and so on, why are they bad? Well, in order to answer that question, we need to look at molecular orbitals. So let's do a molecular orbital scheme. In other words, an energy diagram on which we're going to list all the orbitals from top to bottom for. We already did this for benzene, and we saw that it works out real nicely, and you might want to go back and review the molecular orbitals for benzene. But what if we do it for cyclobutadiene, 4-membered ring with 2 double bonds? We know that that's virulently unstable. In fact, so unstable that it's never actually been made by itself in a stable form. It does appear in a few weird things, and you can make it more stable by putting some particularly stabilizing groups attached to it, but cyclobutadiene itself has never been made. It's extremely unstable. It's anti-aromatic. So why is that? We'll go ahead and construct your molecular orbital scheme as you learn how to do, with sigmas at the bottom, sigma stars at the top, and pi orbitals in the middle. And I will go ahead and do that alongside you, and you may want to pause the video for just a minute while you construct your scheme. Okay, sigma orbitals. Well, total molecular orbitals will be 4, 8, 12, 16, 17, 18, 19, 20. So 20 orbitals altogether on the scheme. That's because each carbon has 4 orbitals and each hydrogen has 1, so that's a total of 20. Of those, there are 1, 2, 3, 4 p atomic orbitals, which means there has to be 4 pi atomic orbitals, and therefore there have to be 16 sigma orbitals, and we'll divide them in half. The 16 sigma orbitals, we'll put 8 of them at the bottom, 1, 2, 3, 4, 5, 6, 7, 8, and 8 of them at the top, 1, 2, 3, 4, 5, 6, 7, 8. These are sigma star, and these are sigma orbitals. Okay, that leaves us with the 4 pi orbitals to put in the middle. Now the question is, how do we arrange them? Do we do like we did for open, uncyclic butadiene, and put them up 1, 2, 3, 4 like a ladder? Nope, we're going to do the same kind of thing we did with benzene. We're going to start with 1 low-lying pi orbital. Then we're going to have 2 more that are degenerate, same energy as each other, just like we saw with benzene. Then we're going to have the 4th one a little bit higher in energy than that, and that's going to be called a pi star orbital. Okay. And notice, remember that frost circle thing we did with the benzene ring, that if you connect the middle of each of these 4 lines, for benzene you got a 6-membered ring, for butadiene you get a 4-membered ring. Kind of magic how that works. It's just convenient, and it is a way of checking yourself on that. So for any size ring, you'll always get if you draw the frost circle, you'll get the same size ring sort of magically appearing in the middle of your energy diagram. Okay, well, what about these 2? I didn't label them as pi or pi star. It turns out that they're right in the middle. They're neither bonding nor anti-bonding. They are going to be referred to as N molecular orbitals, N standing for non-bonding. Okay. Let's go ahead and just take a minute and draw what would those 4 molecular orbitals look like. I'm going to use the same sort of diagram where we're looking down on the top of it. So for the lowest one, this one right here, it's a bonding orbital. It's going to have 1 node looking like a donut on top, and then another one hiding back behind there. Let's call it positive on the top. And then of course the one underneath that we can't see is the negative one, and it has no nodes. Well, it does have 1 node, right, cutting the sandwich in half, so to speak, but we don't even worry about that one because that's always there. Then, what about the next level? We're going to have 2 molecular orbitals that are degenerate with each other. One of them is easy to draw, and that will be because it will have a node going diagonally through one of the pair of bonds opposite each other, and so the orbital will look like 2 pieces on top, one of which is positive, and one of which is negative, and then two pieces on the bottom, where the bottom of this one is negative and the bottom of that one is positive. I think you get that idea. But what about the second one, degenerated? Because it's the same energy, it has to have one node. And to make it different from this one, we have to draw the node somehow fundamentally differently. And what we do is draw it vertically, cutting through atoms instead of cutting through bonds, as that one does. We saw the same thing happening with benzene molecular orbitals, that when we had degenerate orbitals, one of them would have a node cutting through atoms, and the other one would have no nodes cutting through atoms. Anyway, if we then go ahead and draw the orbital pieces, it's going to look kind of like that. We'll have a positive and a negative on top, and then underneath, hiding behind those, is a negative under here and a positive under there. Again, one node, same energy therefore. Notice that this one, all four bonds are made stronger by that orbital, so that's a 4B, or having four bonding interactions. What about that one? Well, notice that that has, this bond is going to be made weaker, this one's going to be made stronger, this one's going to be made weaker, this one's going to be made stronger, two weaker, neither side wins, so to speak, so it's non-bonding. And we'll put an N there, and that's why that's designated as a non-bonding orbital. What about this one? Well, this is one of those weird bonds in which part of it is covered by a lobe, but the other part has a node going through it. And as we saw before with the benzene molecular orbitals, that's neither bonding nor antibonding, so that particular bond is not strengthened or weakened by an electron in that orbital. Same thing with this one, as it turns out, and that one, and that one. So none of the four bonds is made stronger, none of the four bonds is made weaker, and so that is, in fact, a sort of neutral idea or a non-bonding situation. Okay. And then, of course, we have this top molecular orbital, pi molecular orbital, and that's easy to figure out because basically it's got to have two nodes, so therefore it's got to have a node going through there and a node going through there. And if we then draw the lobes, it'll have one lobe there, one lobe there, one lobe there, one lobe there, and then four more underneath, so a total of 8 lobes for that molecular orbital. And the signs will be plus, minus as you go around, and then the opposite signs on the bottom part of that, the 4 lobes on the bottom underneath would be positive, negative, negative under there. So that's the highest one, and obviously it's going to be an antibonding orbital because this bond is made weaker, that bond's made weaker, that bond's made weaker, that bond's made weaker, so 4 anti-bonding, and that's why it's referred to as a pi star. Okay. So, same sort of idea as we saw with benzene, really not a lot different than what we saw with the benzene situation. However, now we're going to put the electrons in, and this is where the difference comes in. So how many total electrons do we have to put into this into this molecular orbital scheme? I'll count the electrons in the molecule. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 total electrons to put in there, which works out because there's 20 orbitals. And where are they going to go? Well, we had how many down here? We had 8 sigma orbitals down here, so we're going to be able to put in 16 electrons there and just save time, and because I'm lazy, I'm going to just draw 2 big arrows there, but we know that that's actually 16 electrons down there. And then we have 4 more to put in for a total of 20, so where will they go? I'm not going to drag out the suspense, you can probably already see what's coming, but 2 of them will go there. Now we have 2 more to put in. Where will they go? 1 there and 1 there, because remember the rule that says you spread out electrons in degenerate orbitals as much as you can. Well, that's what we have to do, spread them out in those orbitals. Now what do we notice about that situation? Unpaired electrons, that's really bad. You never want to have unpaired electrons in your molecule. They are essentially free radicals, and what do we know about free radicals? They're very reactive. You only see them as intermediates in mechanisms. Well, this has not 1, but 2 unpaired electrons, so that's what makes it so unstable. And basically, to cut right to the chase, anytime you have 4, 8, 12, or 16, or any other multiple of 4, you're always going to end up with unpaired electrons in your molecular orbital scheme, and so therefore that's going to be bad. Anytime you have 2, 6, 10, 14, you're going to always end up with everything being paired in bonding orbitals. It will always be a stable situation. Okay. Just for fun, let's do the 5-membered ring situation, both with a positive charge and then also with a negative charge. We can handle them both at the same time and have to redo our whole molecular orbital scheme. And we won't draw the orbitals this time, I'll let you work that out for yourself, but we'll do the energy diagram. Let's look at a 5-numbered ring with p orbitals all the way around and hydrogens all the way around. And let's do our energy diagram. Let's count the total number of orbitals that we will need, counting the total number of orbitals here. And notice that I haven't specified whether that carbon has a pair of electrons and a negative charge or no electrons and a positive charge, because we don't really need to know about the electrons until we put them in at the end. What we need to know is how many orbitals there are, and every carbon will always have 4 orbitals, whether it has a total of 4 electrons or 5 electrons or 3 electrons or some other number around it. It will always have 4 orbitals. So basically that's 5 carbons with 4 orbitals on each, so that's 20, plus an s for each of those, so that's 25. So I have 25 orbitals. Of those, how many are going to be pi orbitals? This is weird because it's an odd number and we haven't really dealt with that yet. But it's going to turn out that because there are 5 p orbitals around that ring, there are going to be 5 pi molecular orbitals. So 5 of them are pi orbitals, and therefore 20 of them are sigma orbitals. Let's divide up the 20 sigma orbitals evenly between the top and the bottom. So we'll have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not 110. 10 sigma orbitals at the bottom, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sigma star orbitals at the top. Okay? Now we have to worry about those 5 pi orbitals that we're going to put in the middle. This is the first time we've had an odd number, so how do we handle an odd number of pi orbitals? Well, what you do always, whether it's even or odd, is you start with 1 at the bottom. And that's always unique. There's never any degenerate orbitals for that one that's the lowest of the pi's. And then you go up by pairs until you run out. And if you run out and you still have another orbital, you put it at the top as a unique one. But in this case, we're going to have 2 more, and then 2 more. And we would, if we had 7, we'd keep on going, and if we had 9, we'd keep on going, and so on. And then if there's yet another one, we put it at the top. But in this case, there's only 5, so we stop at 1, 2, and 2 for a total of 5. These are certainly going to be anti-bonding in terms of whether the ones in the middle are non-bonding or are bonding or anti-bonding. We'd have to actually draw the pictures and find out, how many bonds are made stronger and how many bonds are made weaker. So I'm not going to worry about that right now. I'd have to figure it out. You can figure it out as easily as I can, so I'll let you do that. The key, though, is that we have this set of degenerate orbitals right above the lowest unique pi molecular orbital. Okay. Now let's put in electrons. Okay, so let's start with the carbocation, in which that's a positive charge. So how many pi orbitals do we have, or how many pi electrons do we have to put in there? 2 from that double bond and 2 from that double bond. Nothing from this carbon, so that's a total of 4 pi electrons to put in. 4 pi electrons. Actually, we need to put in the sigmas first, but it's going to turn out, as always, these are filled with exactly 20 electrons, in this case, to fill up the 10 pi orbitals there. And then we're going to put in another, to put in the 4 pi electrons, where are they going to go? Obviously, 1, 2, 3, 4. Again, unpaired electrons. And that fits perfectly with the idea that this has 4 pi electrons, therefore it's an anti-Huckel number, and therefore it's going to be anti-aromatic, very unstable. Now let's just tweak this a little bit and make a pair of electrons on there. So now we're talking about a carbanion. Now that's a negative charge. Hydrogen, 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 and 2 double bonds. Where are the electrons going to go now? How many pi electrons do we have in this case? 2, 4, plus that pair. So now it's 6 pi electrons. Now we just have to put in 2 more into that scheme, because in this one I had 4 pi electrons. Now I'm going to put in 2 more. Where will they go? Everything's paired up, everything's happy, very stable, very essentially filled shell of electrons. And so that is in fact a good situation. 6 pi electrons, Huckel number, aromatic, good, stable. Now we know how to predict stability based on the Huckel numbers and the theory behind it, the Huckel numbers. Thank you for your attention.